This research paper introduces novel strategies for enhancing low-resource speech-to-text translation by leveraging pre-trained OSR models. The authors conducted experiments on simulated and real low-resource setups for language pairs English-Portuguese and Tamasheq French, utilizing the encoder-decoder framework. They found that initializing the ST model with a multilingual OSR system and using the CTC as an additional objective during training and decoding significantly improved translation performance. The model achieved a 7.3 BLEU score on Tamasheq French data, outperforming previous works by 1.6 points. The study identifies various factors contributing to improvements in low-resource setups, including initializations, objectives, and hyperparameters. These findings are crucial for enhancing the efficiency of speech-to-text translation systems, particularly in languages with limited resources. This research paper explores the initialization strategies for low-resource speech translation systems, focusing on the use of pre-trained multilingual OSR models. It discusses various techniques such as joint training and decoding with a CTC objective, analyzing the effects of different initialization options, auxiliary objectives, hyperparameters, and fine-tuning data amounts on the performance of these systems. The paper highlights the limitations of current speech translation models in low-resource scenarios and introduces pre-trained multilingual OSR models as a potential solution. The methodology section outlines the training process for both OSR and ST models based on transformer encoder-decoder architectures. The experimental setup includes two datasets: Tamasheq to French from IWSLT, 22 in English to Portuguese from the How-To dataset, simulating low-resource setups with varying amounts of fine-tuning data. The paper discusses related works, emphasizing the importance of understanding the role of pre-trained multilingual OSR models in improving the performance of low-resource speech translation systems. It contributes to the understanding of effective initialization strategies, identifying key factors that contribute to improvements in performance. The experimental setup and results for speech recognition and translation models are presented, utilizing the transformer encoder-decoder architecture with 27.93 M parameters for monolingual automatic speech recognition (OSR) models and 31.78 M for multilingual OSR models. A custom clone of the ESP.NET framework is employed for conducting experiments. Word error rates (WER) and character error rates (CER) are reported for OSR systems, while 4-gram BLEU and CHRF23 scores are used to evaluate speech translation (STREET) systems. The statistics of data used for OSR model training are provided in Table 3, covering both monolingual and multilingual setups. Table 4 showcases the performance of various OSR systems in terms of WER and CER. Notably, the multilingual OSR model outperforms monolingual models for French, particularly when trained on larger amounts of data. The impact of connectionist temporal classification (CTC) weights is also explored, revealing that higher CTC weights result in lower WERs when training on low amounts of data. For ST models, the authors investigate two initialization methods: retaining the CTC layer for joint training or discarding it for standard training with attention loss. Hyperparameter tuning is performed, examining beam size, CTC weight during street training and decoding, and identifying optimal combinations that yield better performance on the development set. The performance of ST systems on the TAQ right-pointing arrow FR dataset is illustrated in Figure 2, demonstrating the effects of different initialization, fine-tuning, and decoding schemes. This paper explores strategies to enhance low-resource speech translation, combining recent findings from joint training and decoding in OSR and direct speech translation techniques. The authors conducted experiments on the Tamasheq French dataset, utilizing pre-trained multilingual OSR models and achieving a 7.3 BLEU score, outperforming prior works from IWSLT 2022. They also investigated the effect of CTC as an auxiliary objective for translation, which showed positive results, especially when combined with joint decoding. The influence of various CTC weights during training was explored, observing that a higher CTC weight yielded better results as the amount of ST fine-tuning data increased. The authors presented low-resource simulation experiments, aiming to identify the saturation of benefits from pre-trained OSR, given source language transcriptions and source right pointing arrow target parallel data. They trained two source language, N-OSR models on 16.4 and 50 hours of transcribed speech, respectively, and two N-right pointing arrow point MT systems on the corresponding parallel sentences. Using the speech encoder from OSR and decoder from MT model to initialize an ST model, which was then fine-tuned on 16.4 and 50 hours respectively, the authors demonstrated that models based on target language pre-trained OSR outperform the baseline by a decent margin under the low-resource setup of 16.4H. In the mid-resource setup, i.e., with 50 hours of data, the gap reduces to 1 BLEU score. Future research directions include studying the effect of multilingual ST fine-tuning, which should provide additional supervision, thus helping the overall translation quality. Another important direction relates to quantifying misaligned representations when initializing modules from different modalities. The work was supported by Horizon 2020 Marie Skłodowska-Curie Grant Esperanto, Czech National Science Foundation, GACR, Project NEUREM3, and Czech Ministry of Interior Project VK01020132. In the realm of computational physics, researchers have long sought to understand the intricacies of quantum systems and their potential applications in computing. A recent study delves into the complexities of quantum phase estimation, a fundamental algorithm in quantum computing that allows for the precise calculation of eigenvalues of unitary operators. These eigenvalues are crucial in various quantum algorithms, including Shor's algorithm for factoring large numbers. The research focuses on the quantum phase estimation (QPE) algorithm, which estimates the phase phi introduced by a unitary operator U when applied to an eigenstate, psi greater than. This phase is directly related to the eigenvalue of U, providing a means to calculate it with high precision. The QPE algorithm utilizes a series of quantum Fourier transforms and controlled U operations to achieve this estimation. A key aspect of the study is the exploration of different quantum error correction codes, such as the Surface 17 code, which can significantly enhance the fidelity of the QPE algorithm. By incorporating these codes, researchers aim to mitigate errors that arise during the computation, thereby improving the accuracy of the estimated phase. The paper also discusses the importance of optimizing the number of qubits used in the QPE algorithm. An excessive number of qubits can lead to increased error rates and computational resources, while too few may result in insufficient precision. The authors propose an adaptive approach that dynamically adjusts the number of qubits based on the desired precision and available computational resources. In conclusion, this research contributes significantly to our understanding of quantum phase estimation and its role in quantum computing. By developing more efficient and accurate methods for estimating quantum phases, scientists can unlock new possibilities for solving complex problems in physics, cryptography, and beyond.